This is a little web version of a talk that I gave at the iRing Center in early April of 2014. I'm going to make a version and put it on the web. A little introduction to my lab's research. We do research in nucleation and catalysis and also in the fundamentals of reaction rate theory. The methods that we use, the theoretical methods that we use, are a class of rare events methods. And rare events methods are really special. This is a typical diagram showing the multi-scale simulation landscape where you have time scale and length scale associated with different computational methods for studying chemical processes. So you have electronic structure theory that can treat things at very, very short time scales, femtoseconds and picoseconds, and nanometer length scales. And then as you move along this diagonal, you see that you have molecular dynamics, you have kinetic Monte Carlo, phase field models, finite element simulations eventually get us all the way to the macroscopic scale. What I would note about all of these methods is that they really lie roughly along the diagonal in this time scale versus length scale diagram. And if you want to study things that involve very, very short length scales, but can involve very long time scales, for example, the waiting time for a chemical reaction or the induction time for nucleation, things of that sort, then rare events methods are really a unique way of addressing those kinds of problems. And they allow us to circumvent the long waiting times that you typically spend where the system is really doing nothing much interesting, just rattling around in the metastable basin before a activation event happens, and then in a flash it jumps over the barrier and becomes a long-lived product again, right? So if you just run brute force MD, you will find that you spend almost all of your time down here in either state A or in state B, and very rarely see the system make these transitions. When it does make those transitions, they occur very quickly. And what we would like to do, since all of the interesting part of the reaction mechanism is taking place right in here, we would like to have a method that focuses our computational effort on what's happening in this most interesting part of the process. And there were many of those actually throughout the 80s and 90s. There were quite a few of these methods that were developed. But they always required that you chose a reaction coordinate based on your chemical intuition and drove the system along that reaction coordinate by some bias sampling protocol. What was really special about transition path sampling is that it did not require that you choose that reaction coordinate. So it still allowed you to compute rates and transition paths while capitalizing on this time scale separation. But it was able to do so using the true dynamics of those reactive trajectories. And so in a sense, transition path sampling allowed us to directly access the ensemble of dynamical trajectories that corresponded to transitions between state A and state B, for example, reactants and products. But we can generally do this for just about any dynamical process, and that makes transition path sampling in some ways the analog to what Metropolis Monte Carlo did for static instantaneous statistical properties, right? So transition path sampling, that's a bold statement, but transition path sampling really is special, and it allows you to do a lot of really beautiful analysis. And even recently, the Chandler group has extended this to non-equilibrium properties and things like jamming and stuff of that sort. So transition path sampling, I think, is really special, and people were very excited about it. It requires some machinery that looks very much like Monte Carlo. You have detailed balance in the space of dynamical paths. You have acceptance rules for accepting those paths, and you have generation moves for generating new paths from old paths. So it does really all the same things that we did in Metropolis Monte Carlo, except that we are working with paths instead of configurations. Okay, the first algorithm for doing transition path sampling was this one developed by Ballhaus and Geisler and Delago and Chandler and coworkers, and they developed these shooting and shifting moves. This is a ergodic set of moves for sampling path space. And I won't go through too many of the details of how this works because we've since developed moves that I think are a bit more efficient. But anyway, this was the sort of pioneering work that set all of this stuff in motion. So in the early days, people were really excited about transition path sampling and basically thought that it was going to solve everything. And if you read different review articles, you know, Auerbach calls it the Cadillac of reaction dynamics methods, and Manilopoulos has one that refers to it as a Rolls-Royce of reaction rate theories. And people were, in general, just very, very excited about the potential for what could be done with transition path sampling. But over time, in the applications, people started to realize that there were some limitations that were just practical computational efficiency issues for the most part, but still they were pretty severe, right? So Don Frankel pointed out that transition path sampling becomes inefficient when a process takes longer than a picosecond to cross from the top of the barrier down back to the reactant or product state. So when that transition path time becomes long, that's exactly when we need a method like transition path sampling. And what Frankel has effectively noted here is that transition path sampling sort of stopped working exactly in that range where we needed it as an alternative to things like nudged elastic band. There were also issues with the sort of fundamental capabilities of transition path sampling. So Chandler and Chakraborty and coworkers pointed out that while transition path sampling was developed to circumvent the need for a reaction coordinate, the process of identifying the reaction coordinate, which is a very important mechanistic insight that we would usually really like to know, was limited to sort of a trial and error procedure. Okay, so this was something that was really, really needed at the time. That, you know, in order to test whether the coordinate that you guessed was correct, you had to go through this very, very expensive procedure, as noted here by Ballhaus. Each individual test takes a very long time, really hundreds of thousands of trajectories. So I want to sort of give an overview. Probably many people, when they think about reaction rate theory, would naturally and reasonably think, you know, why do you need anything like transition path sampling? Why can't we get by with the theories that we have? Well, there are, for looking at things like catalysis and breaking and making chemical bonds, traditional chemical reactions, reactions in the gas phase, we have some very powerful and reliable reaction rate theories. Things like transition state theory for catalysis and things like our RKM theory for reactions in the gas phase. These work really well. And we have standard algorithms that go along with those theories that help us find transition states. Sometimes we need to augment these theories with things like tunneling corrections or recrossing corrections. But for the most part, these work really well because the only part of the landscape that's really important for a simple process like this is the nature of the landscape in the immediate neighborhood of the pass. As Wigner and Eyring put it, I think they completely understood this problem a long, long time ago and really just needed modern electronic structure theory to tell them the potential energy surface and algorithms to find the transition states, and then they were in business. And we've been using those kinds of ideas for many, many years since, right? So in catalysis, this is the standard procedure for doing things. You go out and you find saddle points, you find reaction rate constants according to transition state theory, and then you string them all together. Maybe you run kinetic Monte Carlo or you build a microkinetic model, and you can do a lot of nice predictive work using these ideas. The reason that these ideas work is because the potential energies landscape on the scale of the bonds that are being broken and formed looks pretty smooth. That is to say, over here the bond hasn't broken yet, and over here the bond is broken and a new bond has formed. And as you move from one basin to another, you really can trace along a nice smooth path that passes through a saddle point that corresponds to the breaking and making of those new and old bonds. Things look quite different when you look at processes like nucleation or protein folding or electron transfer or any reaction in solution, really. So for these kinds of processes, every time a solvent slips past a solute, or a solvent slips past a solvent for that matter, you get a small little bump on the potential energy landscape, and maybe you get a saddle and a local intermediate associated with that. These things are really so shallow that all they serve to do is to disrupt the dynamics. As you move from reactant to product, for example, all the charge over here on the cation on the donor versus all the charge being transferred to the acceptor, that, you know, the reactant state where the donor has the negative charge might correspond to state A, and the acceptor might correspond to state B. And as you move from one place to another, the individual motions of these solvent molecules aren't so important. What matters, of course, we know, is the energy gap from Rudy Marcus's work. But you also find this same kind of characteristic, that there are all these largely irrelevant degrees of freedom among thousands and thousands of candidates that you might pick. There's only a couple that seem to really be important. Same thing for protein folding. You have lots of contacts that can be formed between the native contacts and non-native contacts, and you have coordination of the residues to the solvent and the environment. And in all of these cases, what you find is that you have this rugged energy landscape. And the only way to really make sense of that is to project the rugged energy landscape onto a free energy landscape. Now, if we had Rudy Marcus and he could divine for us the proper reaction coordinate to use for this projection, then everything would make perfect sense and we would get a nice double well kind of problem. We would be able to identify on this landscape a reorganization energy and a driving force, for example, in the case of electron transfer. And we would be able to compute rates from thinking about this. In this case, we've got to also think about the coupling strength to convert this into an adiabatic picture. But anyway, there are some details there. But the important thing is that we can make sense of things if we can find a simple reaction coordinate that will allow us to do a projection and recover something that is comprehensible from this very rugged energy landscape that's really just too complicated to think about. Now, the problem is that we know that if you put the wrong coordinates into one of these projections and use it to compute rates, you get the wrong answers. We've known this for a very long time, going back to work by, for example, Jim Langer in the case of processes that resemble diffusion over barriers, and to Wigner for processes that look like variational transition state theory, ballistic motion over the barrier. Now, if you know the reaction coordinate, you can, of course, go through and you can compute free energy profiles like this, and indeed people have. Warshel did that in his 1982 paper, I think it was. But the problem is that when we're looking at problems like this, we really don't know what coordinates to use. No one has told us what is the correct coordinate yet for these cases. And you can proceed a couple of different ways. You can just choose coordinates, and you can make them up, and you can compute things using metadynamics or umbrella sampling or something of that sort. But of course, you never really know whether you're right, and unfortunately, a lot of groups go ahead and they publish them without testing to see whether they are right. And that's sort of a dangerous thing to do, because we know that you get the wrong answer if you choose the wrong coordinate. And it's surprisingly difficult to get the right coordinate when you're dealing with tens of thousands or maybe even hundreds of thousands of degrees of freedom and looking to pick the right one. So I want to emphasize something that may not have occurred to people, and that's that when you look at these cases right here, the case of electron transfer theory and the case of transition state theory and RRKM theory, these are, by many measures, I would say, the three most successful reaction rate theories that we have. And what makes them successful is that they are simple. They identify these parameters. For example, in the case of electron transfer theory, you have a reorganization energy and a driving force. And we can use these when we compute them to make predictions about experimental rates. But not only that, they're such simple, easy things to think about that experimentalists can interpret the rates that they measure in terms of these quantities. Likewise, when you go over here to, for example, transition state theory, there are really just two parameters. There's an activation enthalpy and an activation entropy. Those two parameters determine our exponential and our pre-exponential factors. And they can be used if we can compute the energy landscape and identify this critical saddle point, then we can use that information to predict the outcome of an experiment. But we can also take experimental data, and without doing any calculations, we can interpret the properties of the transition states and the bottleneck in terms of those quantities. Now, what makes these two theories so successful, aside from the fact that they allow you to both interpret and predict experimental properties, is that, and in fact, the reason that you can do that with these theories is because they are simple. And they are simple because they are the three examples where we know the reaction coordinate associated with the process, right? So here, we know the reaction coordinate is the energy gap. And over here, we know from age-old constructions that the reaction coordinate is to a very good approximation the unstable mode after diagonalization of the second derivative, mass-weighted second derivative matrix at the location of that saddle point on the energy landscape. Okay, so the reason I'm claiming that these two theories have been able to describe so many different reactions and so many different electron transfer processes is because we have a very general and yet accurate and simple description of the reaction coordinate. It's a scalar reaction coordinate. There's only one. There's not many. And it describes things across the whole spectrum of reactivity and electron transfer processes. So with that motivation in mind, how can we begin to find reaction coordinates for other problems? Well, there's been a whole group of methods that say we don't need the reaction coordinate. Let's get rates without knowing the reaction coordinate. And then there's the methods that I'm going to tell you about today, which are aimed at trying to find the reaction coordinate in a systematic way. And actually, these rely on some of the foundations and methodological advances that were developed for doing this. So they're not completely unrelated directions. But what I want to really discourage is just grabbing reaction coordinates from a plug-in and computing free energy landscapes and interpreting them mechanistically without really knowing whether you're doing the right, looking at the right free energy landscape. Okay, so that sort of motivates the talk. I have given the introduction in some sense already, but now that you have a sense for why reaction coordinates are important and what can be done if we know them, I want to tell you about how to get them. Likelihood maximization is the approach that we've used. I should note in fairness that Aaron Dinner came up with one of these called the neural network approach that is quite good as well. So high throughput mechanistic hypothesis testing is the selling point here, and that's this idea that you can generate a whole long list of mechanistic hypotheses and quickly screen through these to figure out which one is the best using some unbiased data. I want to emphasize that there is a very good reason for us as theorists to think about doing this work carefully and not to make stuff up and publish things on the basis of unjustified choices of coordinates. Here is an example of something that the experimentalists say about us. This is the textbook by Davis and Davis, two experimentalists writing about the words mechanism and model. They say that they have largely acquired bad connotations because they are associated with much speculation. So, I'm going to argue in this talk that we can actually do things in a more systematic way and come up with a more quantitative basis for the claims that we make when we talk about mechanisms in computational work. What do I mean by more systematic and quantitative analysis? Well, in terms of mechanistic insight, we can systematically reduce the dimensionality from hundreds of thousands and tens of thousands down to one. In the process, we will be able to preserve the thermodynamics and the dynamics of the process. We will be able to have a compact summary of the transition state ensemble. We'll be able to test mechanistic hypotheses, and we can even go back and begin to test theories of reaction dynamics. Recall that most theories of reaction dynamics are built around an assumed knowledge of the reaction coordinate. To a large degree, many of those couldn't be tested in the past because we didn't know the reaction coordinates. But once we find the reaction coordinate, we can go back and actually put those theories themselves to the test and see whether they describe real systems. And of course, for those driven by computational efficiency, it's been shown time and time again that when you know the correct reaction coordinate, it's vastly more efficient to compute free energy barriers and rates. So all of those are, I think, very good reasons for striving to find the reaction coordinate using this high throughput mechanistic hypothesis testing approach of likelihood maximization. So a few words on efficiency of path sampling itself. We sort of accidentally developed aimless shooting along the way to developing the likelihood maximization approach. Recall, I won't say very many things about the details of how this method works, but recall what Frenkel said, which was certainly true at the time in 2005. He said that transition path sampling became inefficient if the transition paths were longer than a picosecond. Here you see that aimless shooting has been applied to this Lennard-Jones nucleation problem. You're going from a metastable liquid to an FCC crystal. And this is sort of a guinea pig problem in the area of systems with long diffusive transition paths were known to be quite a challenge. And in 2006, we developed this method that later Beckham and I used to show that this method actually can sample trajectories that are very long with really no problems. It handles, in this case, 400 picosecond duration transition paths while still getting 30% acceptance. And these trajectories decorrelate from each other quite rapidly. The trajectories, successive trajectories really look nothing like the one before it, and so that's really quite an advantage over some other approaches. So aimless shooting, I think, really fixes this efficiency problem in transition path sampling. And I should note here that there are some other algorithms. For example, the one-way shooting algorithm of Ballhaus does a pretty good job at fixing this inefficiency problem as well. So determining variables that reflect the dynamics of the system, this is identifying the reaction coordinate, and also testing the reaction coordinate remained a problem. And first we have to specify what do we mean by a reaction coordinate. Well, there's actually a very general definition of the reaction coordinate that's been arrived at now from various theoretical angles. It is that the committer is the reaction coordinate. And so you can define the committer as the fraction of trajectories initiated with randomly distributed initial momenta drawn from the Boltzmann distribution. And you basically count the fraction of those trajectories that go to state B before they ever go back to state A, right? So this is my reactant, my product, and I'm estimating the fraction of trajectories that commit to state B. Okay, so this particular point is part of the B basin of attraction, and so most of the trajectories go back to state B, and I would say that this point is therefore more like a product than it is like a reactant. It's a dynamical definition in that sense, although it only depends on the configuration space variables. If you have a point that has a committer of 1/2, then it would be a point lying right along this dividing surface. That point would be a transition state, and points that are in or at the edge of the reactant basin are going to be reactants. They're going to have committer probabilities of 0. Points that are over here in or at the edge of the product basin have committers of 1, and they are going to be products. So this definition is exact, but it's also abstract and not extremely useful. Okay, so we really don't have any idea what physically makes these trajectories go to state B. All that we know is that they do go to state B, and therefore this configuration is somehow a product. So we can concoct little examples that show what the situation is for reaction coordinates that are good and reaction coordinates that are bad. So you have here a diagram depicting a multidimensional energy landscape. Here multidimensional is just 2, and we have coordinates Q1 and Q2, reactant basin and product basin, and in the space between you see that it looks like Q1 is the degree of freedom that's changing, and so we might project everything onto Q1. If we did that, we would find a double well free energy landscape. If we look right here at the top of this barrier that coincides with position Q1 star, we can now go back to the full dimensional energy landscape and ask what configurations live at Q1 equals Q1 star, and they correspond to this vertical line. Okay, so the points on that vertical line indeed do look like it does look like a good dividing surface that really separates basin A and B, passing roughly through what should be the separatrix for this reaction. Now, situation is different when you look over here at the case of a bad reaction coordinate. So again, the coordinate that's changing when you go from A to B is primarily Q1. But you take this sort of nonlinear path between those two states, and again, if you did a projection onto Q1, you would find a double well. Everything looks like it's behaving completely fine. The problem is that now if you look in the multidimensional space at the configurations that correspond to Q1 equals Q1 star, they are along this vertical line, which passes through the edge of basin A and also through the edge of basin B. And so if you were to compute the committer probability for this vertical line that really doesn't cut the space very well, then what would happen is that you would see a whole bunch of points over here on the edge of basin A that all go back to A. Those have committers near 0. And you have a whole bunch of points that live here on the edge of basin B, and those all have committers near 1. And if we constructed a histogram of the committer probabilities for each point along this dividing surface, then we would find most of them in state A, some of them in state B, and very few points in between corresponding to transition states, right? So These few points in here are actually transition states, but there aren't very many of them because the energy is high and it passes through that region pretty quickly. So the problem with this, and this is really depicting the trial and error approach that Ballhaus noted was so expensive, is that you've invested really something like 100,000 trajectories in testing the coordinate Q1, because each of these estimates requires about 100 trajectories, and you have to look at maybe 1,000 of these points to get a good idea of what this histogram looks like. And so that's a pretty costly process. And we can't recover that data. We can't really do anything with it afterwards. It's specific to the test of coordinate Q1. So what we can do instead is hope that we can find a good coordinate. And if we can find a good coordinate, then this test will come out to say that almost all the points on this dotted line depicting the ideal reaction coordinates isosurface, dividing surface, will be transition states, and that will result in a histogram that is peaked around BB equals 1/2. Okay, so this is the way things are supposed to go if we're lucky and we guess the right thing the first time. The problem is usually we go through a few iterations guessing the wrong things before we get anything that looks anywhere close to being peaked. Can we make the test less expensive? Indeed, you can. You can take the you can take this histogram process that I just described, and you realize that you're not actually computing the real committer probabilities. You're computing these binomial estimates of the committer probabilities. And the points at which you draw them are taken from the real protocol-independent distribution of committers. So we can't actually go in reverse. We can't take our histogram and compute the real distribution. But we can go in reverse to a degree because we can take the histogram and we can solve for the first two moments of this underlying protocol-independent distribution. Okay, so that's I think kind of cute and clever. It allows us to go, for all practical purposes, it allows us to go backwards because the only thing that we care about is that that histogram is that that committer distribution is peaked near 1/2 and that it's relatively narrow, right? Which tells us that we're doing a good job of estimating where our transition states are, and we're doing and we've got not only a description of the sort of bottleneck along that reaction coordinate, but also that it's a good reaction coordinate in the sense that this spread in the committer distribution is very narrow. So we can now begin to say something quantitative, that the committers associated with a given dividing surface along a trial reaction coordinate are centered at a value of mu plus or minus sigma. But the real advantage of doing things this way is that we no longer need these very accurate binomial estimates, right? So remember, this is what made the committer process expensive, is that each time you sample a trajectory, you need something like 100 trajectories. Each time you sample a configuration, you need something like 100 trajectories in order to get a good estimate of this committer probability. Now, the old strategy was to use hundreds of trajectories so that this committer distribution looked a lot like the underlying protocol-independent committer distribution, right? So this is the histogram. We can make it look like the real distribution, which is what people used to try to do, by doing very accurate committer estimates. And then this thing basically looks like a delta function. The problem with that, of course, is that these accurate committer estimates are expensive, and they really drive up the cost of doing this. We can instead do very cheap committer estimates and back out these moments with very high accuracy, it turns out. Using something like 1/10 the number of trajectories is what people used to do in the old test. So why doesn't everybody do this? Well, there are a few groups that really refuse to test their coordinates. I don't think that there should be any requirement that coordinates have to be good to publish the results, but I think that it's sort of honesty in reporting that we want to know whether the degree to which we can trust results that are published. And I think that some are still reluctant to do this test because there's no guarantee that you'll pass this test, right? So this is a way of making the test easy to do, but it doesn't make the test easy to pass. And that, of course, is disappointing when you invest a lot of work in something and then it fails this little test that says there's still a better coordinate out there. But at some level, I think that knowing that really inspires further work in that direction and lets everybody know that the problem is not completely solved. And so I would like to see, of course, maybe I'm biased because I would get some citations out of this, but I think that just for quality of reporting and the desire to report accurate results, it would be nice to see people really be willing to do this test and see whether the results that they're reporting are trustworthy or not. So in a nutshell, this is now we fixed the efficiency problems in the transition path sampling approach, and also fixed the cost, the inordinate cost of testing whether a coordinate is the correct one or not. What remains is to go back and have a way of actually identifying those collective variables that are correct. And the basic idea behind this approach is this mechanistic hypothesis testing strategy. The overall strategy is that we suppose that there exists a simple physical coordinate Q that would be sufficient to predict the outcome of the committer probability, right? So Q depends on the full atomistic configuration, and so does the committer. But what we're saying is that if we just know the value of this simple coordinate Q, which might be a measure of nucleus size, or maybe a dihedral angle, or maybe it's some secondary building structure for a protein, then that quantity Q should be enough to predict what this committer is going to be. We don't actually need to know where every individual atom is. So then the idea of going through and identifying one of these coordinates is that we first have to collect some data that's not tied to any specific coordinate. We want some unbiased data that we're going to generate using transition path sampling. And then what we're going to do is to screen hundreds of mechanistic hypotheses for what could be a good reaction coordinate, and identify among those hypotheses the one that best explains the unbiased data that we got. The final stages, we're going to validate whether our coordinate is correct by using this committer test with the efficient version of the committer test, that is. And then we'll reap the benefits and do all the things that I promised at the beginning of the talk. Reduce dimensionality, preserve thermo, summarize the transition states, etc. So the machinery for doing this is this aimless shooting data combined with likelihood maximization. Now, what I didn't really show is how aimless shooting works, but there's one key property that's really quite important. That is that it generates the shooting points in the vicinity of the natural bottleneck for the process of interest. Okay, so what I'm showing here are not the trajectories. In previous versions of transition path sampling, people were very focused on the trajectories themselves, but actually the mechanistic information is in the shooting points and their outcomes. Okay, so if you see a point that's colored red here, that means that I did a shooting move there, and that the trajectory that resulted from that shooting move went in forward time back to B. And where you see points that are colored green, there was a shooting move executed, and the forward trajectory went on to A. Okay, so there's a clear trend where these trajectories change color as they go from green to red. You're moving in this direction across the saddle point on this simple two-dimensional energy landscape. Now, for most problems, we have sort of 10,000 dimensions. We can't just look at the problem and see which direction corresponds to the reaction coordinate, and we have to have something more systematic. So what we do is we propose a mechanistic hypothesis, and we say if our mechanistic hypothesis is correct, then all of these realizations of the committer probability, each one of these is like flipping a biased coin. Over here I'm very likely to go to B, and over here I'm very likely to go to A. In between, I'm likely to go either of the two directions. So each of these is like a realization of this committer probability. And if my hypothesis about the reaction coordinate is correct, then it should all collapse onto a simple function of Q that itself, now Q depends on X, and once I know Q, that's sufficient to predict PB. So we know some general properties of the relationship between Q and PB. It should go, PB should go from 0 at values of Q that are much before the bottleneck, and it should gradually increase going to 1 as you pass through the bottleneck and on to the product side of the reaction. So this is actually a theoretically motivated form. This is motivated by the backward Kolmogorov equation for diffusion over a barrier. You get a committer probability that's related to the reaction coordinate by an error function. These parameters, because this is theoretically motivated, have a physical interpretation. The inverse A parameter is the width of the barrier top, and the Q dagger parameter is the location of the transition state along your trial reaction coordinate. So now what we do, we have this function that relates Q to PB, and we have a whole bunch of trial guesses for which Q should go into this function, and we have a machinery, of course, for optimizing these adjustable parameters. And what we do is we try every one of these mechanistic hypotheses. We ask which one of them was most likely to explain this unbiased data. And the one that's most likely to explain this unbiased data maximizes this likelihood, where I've taken the committer probability for all the model of the committer probability for all the points that went to B, and the model of 1 minus the committer probability for all of those points that I observed that went to state A. Okay? So we maximize this likelihood, and that identifies the best coordinate among our list of mechanistic hypotheses. So to show you what I mean by high throughput mechanistic hypothesis testing, this is an example that was done with Greg Beckham, who's now at NREL. This is doing likelihood maximization. You have a list here of something like 50 or 60 coordinates that were gleaned from various studies done in the past on Lennard-Jones nucleation, right? So this is this problem that I said was a standard test example. A lot of people have looked at this in the context of nucleation, and they've had different ideas about what coordinates might be important, right? So Greg and I added a few to their list. Those are these size, shape, and size times structure coordinates. What we can do now, after compiling this long list of order parameters, is we can test every one of them individually and in linear and nonlinear combinations with each other. So the results of that are that we have these 60 mechanistic hypotheses. We can test them all in minutes using the aimless shooting data that we already saw once before in the talk for this Lennard-Jones nucleation problem. And what we find is that people were thinking about the right things. Frenkel had a pretty good nucleus size coordinate, but it wasn't really quite good enough on its own. Ballhaus had a good structural coordinate that also wasn't very good on its own. But when you combine these two things in this nonlinear fashion, you get a coordinate that does a pretty good job of describing what is a product and what is a precritical nucleus. And right here along the black line are the predicted characteristics of the critical nuclei. And you can see that when we go back and we test those in the committer test, we find a remarkably sharp description of the committer probability. So the points along this line have committers that are 0.446 plus or minus about an eighth, right? So this is very, very tight resolution on the transition state surface for this very complex problem, right? So we have 40,000 degrees of freedom, and you really only need one to describe its dynamics, and I think that that's pretty remarkable. Many people have used these kinds of approaches in various problems since our work in 2006. You have work by Escobedo and also work by Ballhaus looking at models of protein folding. The one by Ballhaus here is particularly interesting, I think, because while I think it would probably be hopeless to describe the entire process from native to unfolded in a protein folding problem, it is possible, as Ballhaus has demonstrated in this work, to break the folding steps into individual conformational transitions and sort of do things in a stepwise analysis. And what you can do for each one of these individual steps then is describe the committer probability and the mechanism of going from the native state, for example, to this first intermediate fairly well. Okay, so he's been able to demonstrate that, and I think it's pretty nice work. Brandon Knott did a very nice study using this to look at the mechanism of hydrolysis of cellulose by a cellulase enzyme. This is a fantastically complicated process where you have this polymer strand being clipped by the cellulase enzyme. It's sitting inside this cleft in the enzyme, and so there's all these enzyme residues involved, and also, of course, there's chemistry happening. And what I think is really remarkable about this study is that they find a reaction coordinate that, of course, gives them a pretty good committer distribution, but also gives them a pretty high transmission coefficient. And it's been sort of a matter of long-running debate whether transition state theory can tell you much of anything useful about enzymes. And I think that to the degree that factors of 2 are something that we can live with, I think that this is telling us that this is doing a pretty good job with transition state theory after you've found the appropriate coordinate to use in transition state theory. So the key thing here is that they were able to find a good coordinate, and then transition state theory gives them some pretty decent results. There's also studies of acid-catalyzed hydrolysis. and also diffusion of water by hopping in a glassy polymer. So these are also both nice studies where you see that processes that you might be able to describe using transition state theory if you had a good coordinate can also be described using this transition path sampling framework, which finds that coordinate for you. So transition state theory, I think, is of course, pretty powerful tool, and I was giving this talk at the Eyring Center, so I had to bring this back to transition state theory somehow. Everybody probably knows the basic assumptions of transition state theory. You have a dividing surface that separates your reactants from your products, and you have a population of species that live on that dividing surface. These are our transition states, and we assume that they are at equilibrium with our reactant states. Now, technically, this is impossible to do, but it's an assumption that seems to work fairly well for many problems. And the third assumption is that once and this is why it's really impossible to do this, is because you have equilibrium and yet you have fluxes. So the states that live here on this dividing surface, some of them are crossing over to the right. Those that cross over this dividing surface going to the right never return, and they go on to become long-lived products. Okay, so under these assumptions, the transition state theory rate constant can be written in this form. What you'll see here, though, is that the validity of this third assumption really depends on what coordinate you use to compute the free energy barrier and to compute the prefactor. So this was recognized a long time ago, and it inspired the variational transition state theory, which was formalized much later after the early works by Wigner. But anyway, we have a theory now that tells us that you can go in and you can variationally optimize the dividing surface so as to minimize the transition state theory rate constant. In the parlance of more modern theories, people talk about transmission coefficients, and there you have the ratio. The transmission coefficient is the ratio between the true rate constant, which doesn't depend on which coordinate you pick, and the transition state theory rate constant, which does. Now, clearly, if you're minimizing this transition state theory rate constant, and this is an invariant property, then what you're doing is also maximizing the transmission coefficient. So, we can try different coordinates, and we can check and see which coordinate gives us the largest transmission coefficient. The problem is that this is not a very practical approach, right? So it takes a lot of work to compute transmission coefficients. It takes also a lot of work, if you're not just doing harmonic transition state theory, to compute these transition state theory rate constants. You have to compute free energy surfaces, averages to compute prefactors, and all of those things. So this can be a pretty taxing job. And what is, I think, pretty exciting is that there's now a version of likelihood maximization that we published in 2012 that allows you to automatically go after coordinates that give you high transmission coefficients. And this, I'm going to claim, is actually a remarkably practical, easy, and equivalent alternative to doing this tedious VTST approach. Okay, so the hypothesis, the basic structure of the procedure is the same as before, except that now we're going to make a hypothesis that there's a simple physical coordinate that explains not the committer probability, but the reaction probability, right? So the reaction probability is the probability that a trajectory launched with a given position along a reaction coordinate and of a given velocity along the reaction coordinate will reach the product state. So before, we were only thinking about the given position along the reaction coordinate. We were integrating out all velocity information. Okay, here we're keeping just a little bit of that velocity information, and that's the velocity along the reaction coordinate. So this is effectively the same as the construct used in Cramer's theory. It's again going to be theoretically motivated because in Cramer's theory you take a linear combination of the coordinate and the velocity along that coordinate, and you say that that's sufficient to predict the probability of reaching the product state before going back to the reactant state. Now, the data collection procedures in inertial likelihood maximization are exactly the same as before. We use the same data-driven approach. Again, we go back and try a whole bunch of different coordinates and check and see which ones of those coordinates are going to do the best job at explaining the unbiased data that we got from transition path sampling. And in the final stages, we're going to test our coordinates using the committer test, but also we're going to compute a transmission coefficient. And if everything's working well, we should find a transmission coefficient that's very high. This is a little example, a little 12-dimensional example problem. It's a double well potential coupled to a bilinear bath of harmonic oscillators. And what you see is that the original version of likelihood maximization does a pretty good job at finding coordinates that give you very narrow distribution of committer probabilities. So the standard deviation on the committer here is about 0.15 or 0.2, right? So this is a fairly narrow committer distribution, and you would think that everything's working pretty well, except that the transmission coefficients are still pretty low. They're only about a half, right? So we know for this problem from much experience in the past that you can actually find transmission coefficients that are almost 1, somewhere up in the range of 0.95 or so is the limit on the transmission coefficient that you can get for this problem. Inertial likelihood maximization not only gives you committer distributions that are more narrow than those of the original likelihood maximization approach, but it also every single time gives you a transmission coefficient that's very high. And I think that this is really exciting, right? I mean, we've never had a method that can do this in a practical way that really optimizes coordinates over all of space. Okay, so we're still not really optimizing coordinates over all of space, but we can at least optimize them over all of the space that we supply as basis functions. So here is a little example showing an application of this. This is really the first application of this thing. It's done in collaboration with Ryan Mullen, my PhD student, and Joan Shea, collaborator here at UCSB. We looked at this surprisingly difficult problem of ion pair dissociation. So an ion pair can have a contact state, and then it can also, you can have water wiggle its way in between these two ions and create a solvent shared pair. If enough water gets between them and if the two ions start to get far enough apart, we call it a solvent separated pair, and these two ions become effectively independent of each other and completely screened from each other, and they can then diffuse off to infinity and completely lose track of what the other one is doing. So this is the potential amine force for the distance between two ions. Okay, and you would think, looking at this diagram, that right here at 3.7 angstroms, which corresponds to the barrier and the potential amine force, you should have a bunch of transition states. That is to say that configurations launched from a distance of 3.7 angstroms, regardless of what the water molecules are doing, 50% of those configurations should go and form solvent-separated pairs, and 50% should go and form contact pairs. That's actually not what you see. Instead, you see a bunch of configurations where nearly 100% of the trajectories go on to form solvent-separated pairs, and you also see configurations where nearly 100% of the trajectories go back to form the contact ion pair. There are a few transition states in here, which is an indication that this coordinate is not absolutely terrible. But nevertheless, it's not a very good coordinate, and that's sort of a surprise because it means the water is doing something important. In retrospect, so Phil Geisler told us this back in 1999, and in retrospect, looking at this, we really should have anticipated that the water was extremely important for this process. In fact, if you take two ions without water, the potential energy landscape between them looks completely different. There's no barrier. They sort of combine in a barrierless process. So the only reason that there's a bottleneck in here is because of what the solvent is doing, and presumably that makes what the solvent is doing important. So we did some analysis and figured out that that you have a couple of different solvent coordinates that are important in this process. We're able to find a committer distribution that's peaked somewhere in the neighborhood of 0.5, and it's not peaked near as sharply as we would have liked to have seen, but nevertheless it's an improvement on what's been seen before, and we were able to identify those coordinates and develop some understanding of what's going on here. You have basically the number of coordinated water molecules is particularly important, and you have what looks like sort of separate pathways. You can jump from the contact ion pair to the solvent separated pair without a water coordinated, with a single water coordinated, or with two waters coordinated, and each of those has a different bottleneck along the R ion coordinate. Now, what I really want to focus on is not the details of how ion pair dissociation happens, but rather on a rather interesting theoretical question that has to do with Grote-Hynes theory. So it's well known from work back in the 1990s that Grote-Hynes theory does a good job at predicting the transmission coefficient for ion pair dissociation. So basically what you can do here is you can use Grote-Hynes theory. You get a prediction for the transmission coefficient. Grote-Hynes theory assumes that the dynamics is described by this generalized Langevin equation that has non-Markovian friction. That's the key difference between this equation and the one in Cramer's theory, is the non-Markovian friction kernel in here. So once you find this non-Markovian friction, which you can do in simulations by clamping the positions of the two ions and looking at the force-force correlation function on them, you get that friction kernel. Then you can use Laplace transforms to arrive at the Grote-Hynes equation, find the root of the Grote-Hynes equation, which is the so-called reactive frequency, and the ratio of the reactive frequency to the adiabatic barrier crossing frequency is this kappa Grote-Hynes. This is the transmission coefficient according to Grote-Hynes theory. It's a prediction, but you can then go back and you can check with Chandler's reactive flux formalism, which gives you an exact transmission coefficient. You can check and you can find that this prediction of Grote-Hynes theory is really remarkably good for the ion pair dissociation problem, at least according to work that's been done in the past by authors looking at this. Now, what's sort of fascinating is that Pollock and also Hinds himself showed back in the 1980s that you can always take this generalized Langevin equation and you can represent it as the same potential amine force and the same coordinate, but now you couple it to an auxiliary bath of these harmonic oscillators. And if you choose the auxiliary bath to have the right coupling constants and the right frequencies, then you can always make the dynamics along Q in this multidimensional model the same as the dynamics along this generalized Langevin equation. Now, the sort of mathematical model of this is this child swinging on a cart that's on wheels and the cart's going over a hill. Okay, so you can look at this and you can recognize that it's not enough to know which direction and where the cart is at any given point of time. You have to also know where the swinger is, because if the swinger happens to be swinging backwards at the moment when the car is passing over the hill, then the swinger can actually yank the car back in the opposite direction and cause a recrossing of the barrier if you were just using position of the cart as your reaction coordinate. Now, it's important to note that historically the Grote-Hynes theory is typically applied with coordinates that aren't really reaction coordinates at all. They're just chosen coordinates that are used, and what's really quite remarkable about this theory, but also somewhat dangerous, is that it gives you the right answer in many cases, even when it's obvious that the coordinate that's been used for the analysis is not a good one. Now, I say that that's dangerous because you can lead yourself to believe that coordinate is really representative of the mechanism. But in terms of rates, it seems to work really quite well. So what's remarkable about this multidimensional model is that because it has the same dynamics, and because it's a nearly quadratic model, if you make a quadratic approximation to the potential amine force, you can basically recover the results of Grote-Hynes theory exactly from a model that it was harmonic. Now, the new coordinate that you get isn't Q, it's a mixture of Q and X, which I'll call Q prime. So the picture down here is that you have a solute coordinate, which is my quote-unquote reaction coordinate in Grote-Hynes theory, and you have all these bath modes. And you start out using Q as the reaction coordinate, but then when you introduce this harmonic bath, you find out that Q was actually not a good coordinate, and instead you should choose this direction Q prime. Now, because the multidimensional model is basically harmonic, it eliminates, for all practical purposes, the recrossing effects and gives you an exact result from transition state theory alone. Now we know that we can, of course, apply transition state theory to the original coordinate Q and compute the transmission coefficient, and we get the same thing. So this is suggesting that an alternative to Grote-Hynes theory is this multidimensional perspective, and that it's really an equivalent alternative. Now, this result, while exact, has been interpreted in many different ways. So some people have interpreted this result to mean that the underlying system is really something like this coordinate coupled to a harmonic bath. And other people have interpreted this to say, well, this is a heuristic model, and when you find this bath, it is just a sort of a heuristic model that does the same thing, and it doesn't mean that the real system behaves that way. So to the extent that people interpret the results and mechanisms suggested by Grote-Hynes theory as real, and certainly some people have done that, you could argue that that either of those two interpretations are realistic. And so some disagreement has persisted in the literature about this point. Some very brilliant people have argued on both sides because there really are good arguments on both sides. So, some people have argued that the real system, when Grote-Hynes theory works, should have an underlying harmonic bath characteristic associated with the dynamics along that coordinate. Others have argued that really it's just a heuristic theory, this Grote-Hynes theory, and that when Grote-Hynes theory works, yes, you can find this harmonic model, but we shouldn't take it too seriously, that it's just a model. Okay, so what they're saying is that you can have these nonlinear features that still end up giving you recrossing, and that there's no reason to believe that transition state theory as applied using the multidimensional framework is really representative of the real thing. That the real system might still have some recrossing effectively because of nonlinearities. And then these guys counter a very good argument, and they say, well, if you're dealing with a nonlinear model, then you have no justification for writing down a generalized Langevin equation in the first place. And of course that's a good argument too, and it's been very hard to sort out which of these two viewpoints is really the correct one, because we can't actually go and do variational transition state theory and find this real coordinate q prime for any system of true nonlinear complexity, right? So enter the methods that we've developed, and what we did, so actually Mullen, my student Ryan Mullen, came up with this little trick. He said, well, if multidimensional variational transition state theory is actually correct, then it should be possible to find a dividing surface with no recrossing, right? If the argument is that when Grote-Hynes theory is correct, there is a multidimensional model for which transition state theory would work, and recall that several people have actually said this, then if that's true, then it should always be possible in cases where Grote-Hynes theory works to find some multidimensional VTST model that's correct. That can only be possible if there is a surface for which there was no recrossing. So Ryan supposes that there's no recrossing for some dividing surface, and just notes a logical consequence of that. That's that any trajectory that goes from A, passes through an intermediate state x, and goes back to A, cannot also be visited by a trajectory that goes from B, passes through intermediate x, and goes back to B. The reason is, of course, if looking at this picture, you can see that you can never divide space without cutting through one or both of these two trajectories. So that would mean that you have these recrossing events. So what Ryan did was he analyzed the transition path sampling data that we had. This was data using an NVE algorithm so that our thermostat didn't cause any extra recrossing, and he found hundreds of these forbidden pairs, suggesting that really recrossing was rampant in this system, even though Grote-Hynes theory worked. And so that's really, I think, a first example of a first counterexample to this view that when Grote-Hynes theory works, there must be some underlying linear character to the problem. So it appears that Grote-Hynes theory, while it is heuristic and probably an inexact treatment of the problem, can do a pretty good job even in highly nonlinear problems for which variational transition state theory cannot. I want to conclude by saying that really many of these problems in transition state theory transition path sampling had some early efficiency related problems, and many of those have been fixed, and they allow us to do all of these things that I described. I've shown you cases where we've reduced the dimensionality from tens of thousands to 1. In the process, we preserve the thermodynamics and the dynamics. We get a compact summary of the transition states. We can test mechanistic hypotheses and many people's different ideas for mechanistic hypotheses, and we can even go back and test statements made about theories of reaction dynamics. All of this also ties into computational efficiency. I didn't really dwell on that too much, but certainly knowing the reaction coordinate makes it easier to compute rates and free energy barriers. I want to point out that there's an important relationship to coarse graining here as well. So in the old days, people thought about coarse graining in terms of writing down a Fokker-Planck equation, right? In order to do that, you needed to have the slow variables associated with the process. So you could think about an atomistic process. If that atomistic process is a rare event, then likelihood maximization can identify these slow variables for you. And then your all-atom thousands of coordinates problem becomes a partial differential equation that is just a Fokker-Planck equation, a Smolakowski equation in this case, that involves computing the free energy surface and the diffusion rate along your reaction coordinate Q. What's happened when you can write this down and when its properties are accurate is that you've reduced a system from something like 100,000 degrees of freedom down to 1. You've preserved the thermodynamics, and you've preserved the dynamics, which is a very hard thing to do, especially for the newer versions of coarse graining that take all atom systems and generate united atom models of those systems. So these things do a very good job of reducing the dimensionality, but they still leave you with thousands of degrees of freedom, right? So in order to actually compute a rate for this process, you would have to deal with those other 9,999 degrees of freedom in order to actually get a rate constant. They do a beautiful job of preserving the thermodynamics of these systems as you go through this mapping from all atom to united atom. But what they invariably do is they lose the dynamics, right? So if you're dealing with something like liquids, you might be able to recover the dynamics by studying the coarse-grained particles with some additional friction in your thermostat, for example. But if you're dealing with a rare event, it's almost certainly the case that you've changed the spectrum of relative rates in this process and that you will no longer be able to predict the long-time dynamics by doing this mapping. I should credit the images that I'm using here. These are from Greg Vost's review article back in 2007. So this is I think a real advantage to finding the correct slow variables first, is that it really is an alternative version of coarse graining that has the unique capability of preserving the dynamics and going all the way to 1 or 2 degrees of freedom. So in summary, transition path sampling was really amazing, and then there was a little period where it was not so amazing because people were concerned about its problems, and those problems have largely been fixed now by us and by other people's efforts who you can read about in our review articles. I want to thank Ryan Mullen, Bernard Trout, Greg Beckham, Joan Shea. All of them contributed ideas to the work that was done here, and the NSF for funding under the career program. And of course, I originally gave this talk at the University of Utah in their Eyring Center, and so I thank them for that as well. And I just want to again motivate interest in this by pointing out all the amazing things that you can do when you actually know the reaction coordinate for your process.